It's great to be here. I don't know if they pointed this bit out. I actually have a very close tie to Canada because I was born north of Canada in Detroit. And spent summers in Sarnia. So it's wonderful to be someplace with a familiar accent again after all those years in Italy. What I'd like to do is to raise a question that you're expecting from a Jesuit there's going to be a little bit of religion. I will start with one tiny bit of religion and a phrase that had been brought out. Men of Galilee, why do you stand here looking up into the sky? It's a line from the Gospels. Jesus has just gone up into heaven at the ascension, and the angels are saying, come on, what are you doing here? It's also, incidentally, the phrase that the Dominican priest used when he was preaching against Galileo, as in men of Galilee. But it's in both senses of looking into the heavens that I want to talk about today. That's a big question, actually, for anybody who does science or who does art or who does things that are not going to directly put food in your stomach. Why are you doing it? What motivates you? What motivated you to make it a career? What motivates you to get up on a Thursday morning and actually go in and do the long, hard bits of work you have to do? So let me tell you a bit about the stuff I do. I work with meteorites, rocks that fall from the sky. You can actually hold a piece of outer space in your hand. Now, I guess there are a few astronomers in this group. You guys think you're studying stars and planets and galaxies? All you're studying are photons, or maybe, gravitational wave now and then. I get to hold the actual material that came out of a star, to the point where I can even measure the isotopes and tell you R process and S process and things like that. Most of the meteorites come from the asteroid belt, which is kind of the scrap heap left over when the planets were formed. A few of them from Mars, a few of them from the moon. Most of the time, they're out in space. Every now and then, one of them will hit the ground. When they do, if you're lucky, somebody will notice it, somebody will collect it, they'll wind up in a museum, and in principle, people like me can then come in and do experiments on them. But anybody who's ever tried to do experiments on a meteorite that was held by a collection or even a collector knows that the Natural History Museum in London, it's not the Natural History Museum of London, it's just the Natural History Museum, because it's in London. Where else could there be one? The people who run their collection are not called the curators, they're called the keepers, which is to say they won't let anybody else touch them. When I showed up at the Vatican Observatory, I had this long, crazy career. I had 20 years as a scientist. Then I had this goofy idea to become a Jesuit, thinking that I would be teaching at a place like UT. And instead, they ordered me to go to Rome and live in this terrible palace and eat that horrible food, but also take care of 1,000 meteorites, which just happened to be my research. I became my own curator. So I gave me permission to do things that I would allow myself to do with the meteorites. The meteorites themselves actually came to us not because of me, a few of them from missionaries. Most of them are collected by the Marquis de Maurois. I had to, my French is not very good, but I know that the ROI, I follow hockey, so I know how you pronounce that. The Marquis was a nobleman in the 19th century, wealthy, collected meteorites the way that noblemen will do. He paid for them. He bought them from other collectors. He wound up with one of the largest collections in the world, had no children, so when he died, the collection was given to the Vatican, hoping that they would have a natural history museum. For a long time, they just sort of sat in boxes until by accident I showed up. And I realized they are a collector's collection, a little bit of every kind. What can I do with such a collection? I can't do the chemistry of them because other people are doing that, and it takes $1 million machine to do that, and $1 million expert to keep the machine running. But I had known from my previous work that there was a tremendous lack of data on very simple physical properties: density, porosity, magnetic susceptibility, thermal properties. I won't go into all the details, except I'll just mention heat capacity. The capacity of a rock to hold heat. How many ergs go into the rock to make it go up by 1 degree? Very simple, but these meteorites are such an unusual accumulation of different materials that nobody had ever actually measured that. Now, the clever way you measure it is you get one of those $1 million machines and somebody who can actually take care of it. This is actually another Jesuit. He's at Boston College. I've showed this picture to somebody who works in a lab and he goes, "Oh my God, he's wearing sandals in the lab." You can do that when it's your lab. And we have made really good, precise measurements of heat capacity using this $1 million machine, but it uses a very, very tiny sample and it takes, a day to get one. Meteorites are very heterogeneous. How could you get the measurement of the heat capacity of an entire meteorite, not just a tiny, possibly not representative sample? So, imagine, if you will, you have a dewar. If you look carefully, you can see Buzz Lightyear on the other side of that thing. We really have a real dewar, but this one is just transparent. And you fill it with liquid nitrogen. And the liquid nitrogen by itself boils away, and therefore the weight of the dewar and the nitrogen goes down at a steady rate until you drop in the rock. And then the weight goes up by a bunch. And then it starts boiling like mad. And that is the amount of extra nitrogen boiled away as the temperature of the meteorite goes from room temperature to liquid nitrogen temperature. I know how much energy it takes to boil 1 gram of liquid nitrogen. I know how many grams were boiled away and how many grams the meteorite was. I can then give you the average heat capacity of the meteorite. Heat capacity in this range is a very strong function of temperature, but it's a known function of temperature. And so having this average value, I've solved the problem. But more than solving the problem, I've worked out, well, a couple of other things. One thing I just have to point out, where are you getting the liquid nitrogen from? I was a theorist before I showed up. And the Vatican Observatory is located in the gardens of the Pope out in Castel Gandolfo. In the gardens is a working farm, including a working dairy farm. If you have any knowledge of animal husbandry, you know that to get milk from a papal cow, you have to have a papal bull. Only nowadays they use frozen, well, we get the milk because they've got frozen bull semen, kept frozen with liquid nitrogen. Whenever we need some, we just go over and get a bottle of liquid nitrogen for this enormous tank that they've got. Another couple of interesting things. This is the actual setup. There is a plastic thing over the dewar. Why? Because you don't want water vapor freezing on top of the liquid nitrogen. Where did I get the exact size? That was at a €1 store. That thing was designed to hold spaghetti. You'll also notice that the dewar is sitting on a cardboard box because if the scale gets cold, then the measurement. All of these little things you learn how to do. One of the other things that people worry about, if you're dropping meteorites into liquid nitrogen, doesn't it make them hard and then brittle? And the fact is that, yes, if you want to break an iron meteorite, you drop it in liquid nitrogen. So am I going to be shattering? Well, you drop it in liquid nitrogen and then you hit it with a really hard hammer. So as long as they don't have any hammers around, it's not going to. I've gotten measurements of hundreds of meteorites this way. And it's great because I have the data. And it's great because I get to play with meteorites and liquid nitrogen. But that's not a good enough excuse for doing it. What is the real reason why we've been making all of these measurements? Well, we know that the meteorites come from the asteroid belt. We know that the asteroids have their orbits subtly changed by the way that they absorb and emit heat. It's something called the Yarkovsky effect. Look it up. But I could talk about for hours. Knowing the heat capacity is one of the elements we need to know to be able to calculate the Yarkovsky effect, to be able to calculate how much an asteroid is likely to shift in its orbit, to protect us if the Earth is ever going to be hit by an asteroid. But I got to admit, when I get up on a Thursday morning, I'm not saying, I've got to take this measurement or else in 200 years, the Earth is going to be toast. That's not what motivates me to do it. Why do we do it? I mean, why do I get up on a Thursday morning to do it? Two parts to that question. Why does society support me doing it? And why do I myself want to do the work? To do science takes money, takes time, takes talent. All of those things are precious, just as precious as the meteorites, just as tightly curated by the people who've got them. Science only happens if somebody somewhere is convinced that the science is worth the cost. And that's something you can't take for granted. Just ask anybody who's tried to get a grant. That means that the scientific questions that get answered are the ones that someone has decided are worth answering. How do we decide whether a question is worth answering? When it's done right, there will be an organized consensus of white papers of scientists in a group in NASA in the United States. There are, every 10 years, the planetary scientists and the astronomers get together and work out a decadal program, a 10-year plan. These are the priorities. And then given those priorities, you and you and you will propose to a mission that will attack them, and the rest of us will be in a committee and say, I think that one, maybe. I think that one's got the best likelihood of succeeding or the lowest likelihood of failing, which is not necessarily the same thing. In the old days, which I've been around for, what happened was you and you and you came up with a proposal, only you happened to be from Maryland, which was the home of the senator who ran the Ways and Means Committee, who decided that they wanted the money to go to Maryland, the Johns Hopkins University. That's how New Horizons was funded. And you say, oh, they found some really cool things in Pluto we didn't expect, which is very true. But because we went to Pluto, we didn't go to Europa. And we'll probably get to Europa now, 30 years later. I'm probably not going to be around to see the results we get from Europa. The cost is more, though, than just the cost of paying for the scientists. You've also got to find the scientists who want to do the work. A zillion years ago, I gave a talk at the College of Charleston, South Carolina. Very good small college. And I was talking about the moons of Jupiter and the geology of that. And the kid comes up to me afterwards and he says, this is great. I go, yeah. He was an undergraduate trying to figure out what he wanted to do. He says, I would love to be a geologist. And I go, well, that's my background. Despite what she said at the beginning, I'm not a physicist, I'm a geologist of other planets. Actually a geophysicist, so it kind of works. But my degree, anyway, MIT people in the audience, my degree was course 12, not course 8. The kid comes up to me and he says, I want to be a geologist. And I say, geology is a great thing to be. And then he says, okay, so what do I tell my mom? And I'm thinking, there's good jobs. No. South Carolina. If he becomes a geologist, his mom is going to think he's become one of them, who is rejecting her culture, her religion, her beliefs, her very narrow sense of her theology of 7-day creation, which is not really a scientific principle as much as it is a flag of where I stand in the culture wars. And for those of us who have never had to face that, you can roll your eyes. But if that is your family, it's going to be really hard to do a job and to have a career that your mom is going to be ashamed of you for. Society has a big effect on what we do and how we make these choices. Scientists are people. People have families. They have desires. We have this mixture of reason and heart, and reasons that reason does not know. And we have to answer those desires in ourselves when we decide to become one kind of a scientist or another, or to say, I did this, it's time to shift into something else. Issues that I'm sure everybody in this room has had to face at one time or another. There is this temptation to divide ourselves into, reason versus emotion, Kirk versus Spock. Actually, if you know Star Trek, Kirk is not all emotion. He's very clever. And Spock is a mess of repressed emotions. Because it's on the basis of both reason and gut feeling that we make the decisions we make. Look at that, the student in South Carolina. If he's going to choose between what he wants and what he thinks his family and his community wants, it's going to be a really tough choice. Now, in my business, the MIT ring and the collar, I get asked about faith and science all the time. And the weird thing is, of course, having lived it, the hardest part for me to really grasp in faith science issues is, why does anybody think there's an issue? I do it, right? Empirical evidence that it happens. It was, in fact, however, talking to Captain Kirk a few years later, that long story how I wound up meeting him, he raised the issues in ways that I hadn't realized before. He says, there's a big book of facts that's science and a big book of facts that's religion, and what happens if the one book contradicts the other book? Now, I think people in this room, that science is not the big book of facts. Science is not the answers to the odd-numbered questions. When you're making your students do that, you're teaching them scales, you're not teaching them music. You got to learn the scales. You got to know how the fingers work before you can make the music. I don't know any other way to teach science. But if you stopped there, you would think that science was just getting the facts in the book. And for those of you who may not practice a religion, maybe you wound up quitting religion at the point where you had only been learning the scales and not realizing that religion is this falling in love. Science is this falling in love. And if you've ever fallen in love with somebody, if you have a great friend or a spouse or a child, you know that you never think you've got them solved. They're not just the answers to the odd-numbered questions. Let me give you an example of the difference. I mean, this is something that I think is kind of obvious, but we never think through. So let's go to astronomy. We've got the Ptolemaic version of the planetary orbits, and we've got Kepler's version of the planetary orbits. And we all know Kepler's better, and Kepler is better. But what was Ptolemy doing? Ptolemy said that I can reproduce all of the odd motions of the planets going back and forth by assuming that the Earth is the center point, and these things are in a circle around the Earth, but that's not quite right. So I'll add a second circle to move back, but that's not quite right. So I'll add a third circle on the second circle, on the first circle. And if I have an infinite number of circles, we call that a Fourier series. And you can reproduce any shape. If you go on the internet and you go Ptolemy, Homer, Simpson, somebody has drawn a picture of Homer Simpson using Ptolemaic, epicycles within epicycles within epicycles. This gives you a perfect reproduction of the paths of the planets. This is going to be wrong in about the 4th decimal place because it doesn't include the effect of one planet pulling on another planet. Which is the better system? We still say Kepler's better. Kepler is better not because it's more accurate. Ptolemy is in fact more accurate. Kepler is better because out of the simple equations of Kepler's laws of the orbits, Newton can come up with the laws of gravity. You can come up with an insight, a deeper insight into how science works. Science isn't about getting the right answer. Science is about coming up with the deeper insight of how science works. That's actually true about faith, by the way. You know, faith is not reproducing that you're getting the answers in the catechism. That's where you begin. That's not where you end. I was talking to William Shatner. I'm trying to figure out how can you mean your religion doesn't tell you? Of course, my religion doesn't tell me anything. And you're not certain. Well, of course, I'm not certain. I'm not certain. You're not sure about God? Neither am I. Neither is anybody. There's a great religious writer, Anne Lamott, who put this marvelous phrase: the opposite of faith isn't doubt. The opposite of faith is certainty. If you're loving somebody and you're sure that they will return your love because they're the robot, you programmed them that way, that's not real love. It's when the person always has the possibility of saying, I've had enough, I'm walking away, and they didn't. That's the miracle. That's the love. Sometimes people say that, science is based on facts and religion on emotions or things you must memorize. Read your religion. Moses gives the 10 Commandments to the people, and then you read the scripture, which a lot of people don't seem to have done, then says, do not forget the things your eyes have seen, or let them fade from your heart. Teach them to your children and their children after them. It's not close your eyes to it. That's not what blind faith is. Blind faith, this is what the argument I had with William Shatner. Don't you believe in blind faith? Blind faith isn't closing my eyes to reality. It's knowing that I have to make choices even when I'm blind. Not because I've closed my eyes, but because I just don't have the data. I'm not sure what the best school will be for me to attend. I'm not sure what the best major is going to be or the best place to live. And I don't get a do-over. I can't live my life and say, oh, should have done that one. We are blind. We will never have the facts. Faith is how we deal with making impossible decisions on the basis of inadequate data. My student in Charleston, South Carolina, is going to choose geology or not choose geology as an act of faith. Not because he found the answers in the Bible or he's reasoned them out with, AI, but because he has incorporated all of that into the human person, which is this mixture of faith and reason, this mixture of emotion, desire, and cleverness. Those decisions made with inadequate data not only change your life, but your life-changing emotions are made by stupid teenagers. The guy with the beard was my roommate. The guy with the goofy hair, that was me, graduating from MIT. Now, how did I wind up at MIT? I was 18 years old. I'd gone to the Jesuit high school in Detroit. I had no idea what I wanted to do. Maybe a journalist, maybe a lawyer, maybe I'd write science fiction stories. I didn't know. I went off to Boston College, and it was a drinking school, and I don't drink. Not because there's anything wrong, but because the stuff tastes terrible. And it's expensive. And it makes you do stupid things. And I can do stupid things without having to drink terrible stuff and spending money. All that money I could have been spending in chocolate. So my best friend was going to MIT at the time, and MIT had tunnels you could explore and weekend movies. And I chose planetary science because I figured engineering was too hard in one way and physics was too hard in the other. And really, I wanted to read science fiction stories, and planetary science had the word planet in it. It turns out to be geology. I didn't know that. Turns out to be studying rocks. I didn't know that. It turns out that there are rocks from the sky called meteorites. I didn't know that. They accepted me, and I was ecstatically happy, like a way I didn't even think would be possible. It's not just that, okay, this is what I'm good at, but rather I'm also around people who appreciate who I am. I'd found my passion. It wasn't science fiction, it was science. It wasn't the tunnels, it was exploring. It wasn't the movies, it was the imagination. And it wasn't the work, it was part of being a community of fellow nerds. You know, I thought I would be an imposter if I'd been in the physics department. It turns out everybody in the physics department thinks they're imposters. There is the right kind of imposter syndrome and the wrong kind. The wrong kind is, oh my God, they're going to find out, and then what'll I do? The right kind is, when they find out, boy, they're going to feel foolish that I fooled them all these years. But, you know, for every Harry Potter fan who wishes they could do magic, I think more of us wish we could be in a school where we know we've been sorted among our friends. For the Lord of the Rings, it's not the ring, it's the fellowship. Science is sharing stories about what we've learned in the natural world. To share the stories, you have to have a community. Without a community hearing your story, you're not going to have anybody to tell it to. And it's not just the stories about where I'm going to go to school, but the adventures you had in the lab or with the telescope. If you don't have anybody to share the stories with, you're going to lose that desire to get up on a Thursday morning and make more discoveries. So it's not only NASA deciding that we're going to fund this program, but it's the community saying, I think Pluto is really worth observing, in spite of the fact that it means we don't get to go to Europa, or vice versa. That's why it makes a difference about what your society thinks, how you, well, to beat this dead horse, India has got the largest population in the world. In India are the highest mountains in the world. Among those mountains are a lot of places where you can go skiing. How many gold medals has India won in the Winter Olympics? 0. How many medals of any kind have they won in the Winter Olympics? 0. And it's not because people in India aren't athletes, you know, ask anybody who plays cricket, but there is not the infrastructure of moms who will drive their sons to the hockey rink at 4 in the morning, the only time they can get time, or will watch their daughters, you know, fall over and get up, or an infrastructure where if you wanted to learn this, you would have somebody who could teach you, or an infrastructure where after you've done it, you can get a job teaching the next generation, or an infrastructure where your mom's going to be proud of you. India, incidentally, was way ahead of anywhere else in the world when it came to mathematics. The Arabic numerals were not Arabic, they're invented in India. The Indians had, this was an observational observatory in the 1700s, which it didn't have telescopes, but it was like Tycho Brahe's observatory. It had ways of measuring star positions, and they had ways of calculating eclipses that were just phenomenal. But they didn't develop what we call natural science, nor did the Chinese for all of the wealth of their empire. If you're Chinese, the highest achievement was to be a person of culture. For an Indian, the highest achievement was to be someone who could calculate. For the Manichaeans in ancient Rome, the physical universe is evil, a source of temptation. Chocolate was devised by the devil to make you fat and give you acne. but to the people of the book, the Jews, the Muslims, the Christians, where we've got a story of creation that says the universe was made deliberately by a good God who says it's good, or as a friend of mine says, God's really saying, yeah, that works. And who is revealing himself in the universe, then it means studying the physical universe just for its own sake, not to, we didn't go to the moon to make iPhones or Tang. We went to the moon because it was a cool thing to do. Chocolate is not this evil thing. It is a foretaste of the goodness of heaven and should be treated like a sacramental. We believe in a God, as Christians in particular believe in a God who so loved the world that he became part of it. And the irony is that there are those who would call themselves Christians who say we shouldn't do science because they haven't read scripture. They haven't read St. Paul, who says, since the beginning of time, God reveals himself in the physical world. End of sermon. I just bring that up because it's part of the job. To get back to the why do we do things, which is the real point of this. Why do we become a scientist? When I was 30 years old, I was a postdoc at MIT, 3 years a postdoc there, and had 2 years previous a postdoc at Harvard. Enough people here to know that 5 years as a postdoc means couldn't get a job. And I'm 30 years old and I'd gone to this Jesuit school and I'd had this religious training. I was not a Jesuit yet. And I'd lie in bed wondering, why am I doing science when people are starving in the world? And I didn't have an answer. So I joined the Peace Corps. And I joined a group of Peace Corps volunteers, about 80 of us. We'll see if I can do this again. And as we're learning Swahili, we'll take a 15-minute break and we start playing hacky sack. Are you familiar with hacky sack? It's this game where all you do is you kick the thing up and you got to kick the other one, you pass it to the next. One of the volunteers came from New York City. Her boyfriend shows up to visit for the weekend. He's watching us play hacky sack and he goes, I don't get it. You're not knocking down anybody? You're not trying to steal it from anybody? How do you win this game? So that is the question ultimately when it comes to doing science. How do you win this game? I hope you're familiar with the PhD comics. This is an old one. When you're in your first year of graduate school, your ambition is to win the Nobel Prize. By the time fifth year of grad school, you just hope that they have pepperoni pizza. And science is like hacky sack. It's a cooperative activity. You gain status by how much you give, not how much you take. You try to keep a lot of ideas up in the air and you pass them around to each other. There's never a moment where you say, I won, you lost. So what is your personal goal if it's got to be more than pepperoni pizza? There are a lot of obvious criteria that a university might use to decide to give you tenure. You're getting approval, you're getting grant money, you're getting prizes, you have successful students, your publications are cited. Are any of those in and of themselves sufficient to make you do the science? Because if you look at them, an awful lot of them are saying that the reward you get for doing good science is that you get to do more science, which is kind of circular. So why are we doing it? Well, there's a different sort of, none of those are what's going to make you, this is a long, I'll skip that whole point. Maybe you're doing it to satisfy curiosity. Maybe you're getting this pleasure in solving problems, in finding patterns. Maybe you're doing it because you always wanted to be the smart little kid and your mom and dad can be proud of you, the opposite of the kid in Charleston. Are these worthy of being ends in themselves? Hey, if we didn't love the work, you could say, but love is kind of, how do you quantify that? And why science for finding love? There are a lot of other places you can find love. More, which of the ones on the left would you sacrifice to get the ones on the right, or vice versa? If you're a committee trying to decide to give tenure to somebody, are you going to give it, well, this guy didn't write any papers, but boy, he's really curious. If you have the chance to get a job doing something you love, but it doesn't pay enough to support your family, what are you willing to sacrifice on that list to be able to get this? It's not always obvious, and different people are going to have different answers. For some people, the academic freedom to study anything they want means that they'll be happy working in a job in a research institute that has a lot of freedom but not a whole lot of money. And other people will say, I just love playing with the stuff, and this corporation will give me a really cool sandbox to play in. And not one of those questions is going to be right or wrong for everybody. But would you give up the approval of the others to satisfy your own curiosity? We saw that when, I'm going to do a bit of science that nobody else is interested in. Does that make me noble, or does that make me a crank? Am I going to give up tenure to satisfy the approval of my families? Am I going to give up fame to satisfy the pleasure in finding patterns? Am I going to give up grant money to satisfy the truth? Where's your heart? Just another way of asking, where's your God? What does that tell you about what you think God is, what kind of God you worship? So why are we doing science? There are internal motivations, but there's got to be something bigger than that. There's got to be something that makes it worthwhile. And if you don't have that sense of what it is you're doing it for, you're going to wind up doing a lousy job of it, because you're going to forget what it is you're doing it for in the first place. And that's at least correct, but I've lost the, okay. About 20 years ago, I had the chance to teach at Fordham University, really bright kids. And I said, let me teach second semester physics, because that was a really important class when I took it, because that's where I learned Maxwell's equations. And these are really bright kids. So I'm writing, finally, I've talked about all the different laws of electricity and magnetism. We've got them in differential form. We've got the 4 equations. We start taking the derivative of the one with the derivative of the other. How many people here are not familiar with Maxwell's equations? Be honest. Okay, about half of you. Fair enough. They're equations. They're the change of the electricity with time makes a change in the magnetic field with space, and Maxwell does a whole bunch of mathematical manipulations and says, looking at these equations, I think there's a piece there that nobody's noticed. I'll bet you looks like this, and adds that in. And after you do all the mathematical equations, you wind up with 2 equations, one just about the electric field and one just about the magnetic field. And they're parallel equations. They say exactly the same thing. The change of the field with space is equal to the change of the field in time times a constant. Yeah, so I had a kid in the front row who's looking at this, who has no idea where I'm going with this. And he goes, wait a minute, I remember that equation from a month ago. And out loud to the entire class to hear, he goes, oh my God, it's a wave. And that's exactly what it is. Because those equations tell you that the electric field and the magnetic field can propagate like a wave, and that constant tells you how fast the wave is going. It turns out to be the speed of light. What propagates like a wave and moves at the speed of light? A light wave. And suddenly we know what a light wave is. And what can I do with this? I can set up a long stick with a wire and make the electrons go up and down the wire and create an electric field, which is now propagating like radiuses in every direction, we call that radio. And by fluctuating the amplitude, I can send signals on that radio. I can set up wires that create an energy flow from the ground to the wires and transport electric power from Niagara Falls to New York City, thanks to those equations. I can look at a distant planet and see that the light of certain colors is absorbed because there are dipole atoms of just that frequency that absorb just those lights, so that me with a telescope here on Earth, I know that that planet must have those particular kind of molecules, those particular kind of atoms. And actually, if you push it far and far and far and far enough, you wind up with quantum theory and general relativity, all of coming out of those equations. It is an oh my God moment. And I say that's why we do the science. Ultimately, it's for the oh my God moments. And here are some oh my God moments that astronomy gives us. The pictures are gorgeous. Can somebody turn the lights off so we get just the pictures? The pictures are gorgeous. The science behind the pictures are just as gorgeous. That's a solar system being formed in a way that was theorized 50 years ago when I was a student. I never thought I'd see it. Some of these are space telescope. That's a Webb picture. Incidentally, if you want to know if it's a Webb picture or a telescope, you look at the spikes in the stars. If it's 6 spikes, it's Webb. If it's 4 spikes, it's Hubble. And this is our own telescope in Arizona. The universe is full of this incredible beauty. And it makes you go, oh my God. And it makes you want to get closer to it. The best example I can give is I love looking at the Great Lakes. I grew up in Lake Huron, but I want to go sailing on the Great Lakes. I want to go diving into the Great Lakes. It's not just enough to look at them. That's how I get my oh my God moments. And incidentally, this is a space picture of a different sort. That's a meteorite thin section. That little chondrule there is less than 1 millimeter across. So you see beauty at every scale. I was mentioning being a postdoc and wondering why people were starving in the world. And so which is why I joined the Peace Corps. What I found out was that even the school kids I was teaching in Kenya wanted to know astronomy. They were excited by space. I had a high school that the president of Kenya came to visit, and these kids put together these models of spaceships and explained to President Daniel Arap Moi why Kenya should be the place where people launch into space. You're on the equator, so you have the maximum velocity of the spin of the Earth. You can launch to the east so that when your rocket blows up, not if, but when, it lands in the Indian Ocean and not in somebody's head. Funny thing, after the president heard all of this, one of his entourage, this very stately woman, walks up to the kid who's giving the presentation, gives the kid a big hug. And the kid's going, oh, Mom, not in front of my friends. And you realize that people are the same everywhere. Teenagers are the same. We're the same. We need to feed our souls. We don't live by bread alone. I'd read that someplace. When I would go up country and, I had a handful of slides and they, showing that NASA had discovered, everybody had the same questions. When we looked through a telescope, how many people in this room have ever seen the moons of Jupiter in a small telescope? Yeah. How many of you have ever seen the rings of Saturn in a small telescope? How many of you have ever seen the rings of Saturn in a small telescope and not gone, oh, wow? Because that's what human beings do. I had a really clever cat when I was in Kenya, but my cat never wanted to look through the telescope. Feeding your soul with the oh my God moments is what makes us human beings. There's the rings of Saturn story. Hearing stories about going to the moon. We sent a spacecraft to the other side of the moon 2 weeks ago. And by we, I mean everybody in this room, because we are all part of the community that did it. And not just because an astronaut was a Canadian. Because it's also true of the people around the world who grew the bananas and shipped them to America to feed the moms of the people who cleaned the rooms. That, the whole community made that possible. And that's why I go into the lab every day. Because eventually I'm going to measure my heat capacities in 2 different ways and see if they make a line and notice that actually they're kind of offset. Oh, I've learned something new. I'm going to get a paper out of this. I'm going to tell my friends at the next meeting of the Meteoritical Society. And we'll argue about what's going on. Is it just bad data? Is it, or is there something functionally happening in the meteorites that they have an unknown element with a high heat capacity that throws all, I don't know yet. This is why the Vatican has an observatory. This is why Canada has an observatory. This is why the University of Toronto has an observatory. And why, well, it'd be really cool to have a planetarium. Thank you, everybody, for showing up.
Wonderful. Yeah, we were going to offer a chat. I don't know if that's on. This is probably the one that's on. I'm supposed to know how to do this because I work here. I don't think it is.
I'll tell you what, shout out the question. I will repeat the question, and that way that way the people online can find it. Yeah. No. But not only that, I can then change the question to the one I know the answer to. Right.
I just wanted to say before we get to the Q&A that as the Fields Institute representative, we're delighted to have us here tonight. And thank you very much. And that I've been invited to talk on a panel about why we do science in about a week. And I'm just going to steal this.
Good.
Excellent. Questions, please. Raise your hand.
It could be about anything from the research to, what's it like to work with the Pope to, what's the difference?
Start with that?
Yes.
What's it like to work with the Pope?
I'll tell you, 20 years I was an astronomer working on NASA grants. You do the work that NASA says they'll pay for. Okay, that's fine. Usually it's good work. But you got to have a result after 3 years or you're not going to get your grant renewed. When I showed up at the Vatican Observatory 30 odd years ago, the boss then said to me, Guy, here's your job. Do good science. And it's up to you to decide what's good science. And it's up to you to decide how long you have to work at it before you got something publishable. It took about 10 years to come up with the database of meteorite physical properties that covered enough meteorites. In the meanwhile, I got to travel around the world. And even better, I got to find another guy to do the hard work because he was better at it than me. But we've got this database now where the guy who I'd hired in to follow behind me, Bob Mackey, was invited by NASA to make these measurements on the Bennu samples. It's not like he, please let me. He says, no, please, would you do this for us? Because it was work that the first time I presented the density porosity work, one of the grand old men in the field came up and said, Guy, why are you doing this? Nobody does this. Which in a sense was a good question if you don't have the community then. But also that's why I was doing it, because nobody was doing it. I had been a theorist. I knew we needed these numbers because I was making models and I needed the numbers to stick in the models and nobody had measured the numbers. So I finally measured the numbers and I'm no longer a theorist. But we need both. We need the people who have the big ideas and we need the people who get their fingers dirty. I was at a meeting of scientists in Europe. After the meeting, we're all from all over Europe, all speaking all different languages, but English is the common language. And we're sitting around in the bar drinking coffee because it's Italy. And one of the guys goes, I hate terrorists. Terrorists are obnoxious. They think they know everything. They never listen to you. He's going on about how terrible terrorists are. And finally, I realized he couldn't pronounce the TH. That's not a good attitude. We need all of this community. And we had another guy, a mathematical physicist, who decided string theory looked interesting. And he spent 5 years digging into string theory and came out saying, nope, I don't think so. And he's doing something else. He didn't lose tenure over it. He didn't, he had other projects going, but still, he was free to be able to do that. And that is the remarkable thing about working for the Pope.
Okay, let's start back with glasses.
Right.
Just yell it out.
Yeah, the guy with glasses kind of, describes 2/3 of the people in the room. Right. The gray-haired guy with glasses. Okay. He was saying that it's my fault that he's in astronomy because of turn left. There was a guy who's starting graduate school at Arizona. Where did it come from? Yeah. How did that fit into the life story? I'll mention, I met a young grad student just starting at the University of Arizona. I got into astronomy because of your book. And I'm going, don't blame me. I know what grad school is going to be like. I showed that little telescope that I took with me to Kenya. I have a great friend, a fellow named Dan Davis. He was a grad student when I was a postdoc at MIT, working for the same guy, a fellow named Sean Solomon. And we found out that we had this common interest in astronomy. And when I knew I was going to Kenya, he drove me into Manhattan and said, buy this, take this with you, it'll fit in your suitcase. And I had this glorious telescope and I could find about 5 things. And afterwards, there's 1,000 stars in the sky. I have no idea which one to point it at. I did have another book, which if there's any astronomers in this room or people who have kids, I hope you know the H.A. Rey book, The Stars. H.A. Rey was the guy who wrote Curious George. Best book. And I wanted an H.A. Rey book for a small telescope. So Dan and I wrote that book together. We had many adventures. I could talk for an hour about that. One in particular was published by Cambridge University Press. And the first edition was full of mistakes. And they priced it in pounds such that it could not be carried by a bookstore in North America because it was $2 more expensive than stores because they had just done it in pounds and then converted. And basically, we worked on this book and it sold a few thousand copies and that'll be it. I happened to be in the United Kingdom. I visited the publisher. I talked to the editor, is there any chance of getting a second edition with some of the mistakes cured? And he's going, well, okay, but what are you doing here now? Where are you? I said, I've joined the Vatican Observatory. He goes, oh? And I said, yeah, I've become a Jesuit. And he goes, oh? He was a left footer, a Roman Catholic. He cleared all of the barriers to make sure that the second edition was perfect. And the book has now sold 250,000 copies. So there is a connection between Vatican science and so, yeah. Right. And then the woman up here had also wearing glasses.
I wanted to ask, what do you not know about meteorites that you still want to know?
What do I not know about meteorites? Why are there meteorites? This is a field of, there are a few mathematicians in the room. You know what a Klein bottle is? Have any of you ever gotten a Klein bottle? You can order them. You can order them from kleinbottle.com. The guy who makes those was a fellow grad student of mine. And as I was describing the work I'm doing with meteorites, he asked me that question. What do you mean, why are there meteorites? So from the outset, no, he says, you've shown that most meteorites are very well compacted rocks. We know the solar system started in a cloud of gas and dust, and now we've got rocks. Where did the dust turn into rock? Why is it that we don't just have interstellar dust bunnies, but we actually have interstellar? And it's a harder question than you think, because you can show and actually discover in space that left to its own devices, solid material will make this very, very loose stuff that's about 80% porous. If you collapse something from 80% porous to 0% porous quickly so that the heat can't escape, the 1/2 mv squared of each bit of rock hitting the other bit of rock creates enough heat that it will melt the rock. And these rocks have never been melted. On Earth, we make rocks because of heat or pressure or water, the three things that the meteorites have never experienced. So why are they rocks? I don't know. Question up here, yes.
I was curious, I was curious what other sort of research has been done.
What research is going on at the Vatican Observatory? First of all, you have to realize we exist as a PR stunt. For the last 130 years, we're there to show the world that the church is in favor of science, supports science. Unfortunately, that's a more needed message than ever. But we're happy to, I'm a missionary for science out in the world. To do that, we've got a dozen Jesuits, and they all have to be Jesuits because we're all living in the same community under the same rule so that we can all live with each other without, killing each other. I had friends who tried living in communes, and that doesn't work. But they come from 5 continents, PhDs from many, many different universities. Everybody comes in with their thing, and then the colleagues that they met at the university. So there are a dozen Jesuits, and another dozen who are affiliated with us. We're not paying them, but they get to use our facilities. And let me give you 5 different experiments that are going on. The guy who decided not to do string theory is working out the mathematics of quantum gravity using Regge calculus. That's as much as I know how to say. I can't even pronounce the rest of the words. We have a fellow who did his degree at Western, by which I mean Western Ontario, is an expert in meteors, which is what they do, best in the world. He worked out how you can use the power and the length of a meteor strike to work out the density of the meteor, the physical density of the rock, and correlate that with the orbits to see which meteors come from which kinds of materials. Kind of cool stuff. A third thing, I mentioned the guy from Benham, so I can't use that. Our director is from Goa, who did his postdoctoral work at the University of Michigan. And he looks at the motions of satellite galaxies. If you've ever seen Andromeda, you know that there's also an M33 and an M33 is a totally different one. What is M10? And again, there's at least 3 obvious satellite galaxies to Andromeda. You can measure their motions. You can figure out where they came from. You can calculate backwards at what point did Andromeda, swallow another galaxy, and are these the leftover bits? The work is so interesting. It was the cover of Sky and Telescope a couple of years ago. We have an adjunct astronomer, an Italian woman working in California. She's from northern Italy, came from a family with no education, and she's got a doctorate doing this stuff. She is running the data analysis group for the dark matter experiment that's being held in the gold mine in South Dakota. And she comes from this little town in Italy, which you have heard of. She grew up in the town of San Pellegrino. Right. Yes, right. And there's an observational cosmologist who uses radio telescopes to look at the strength and the orientation of the energy that came out of the Big Bang. He's not being paid by us. He's working at this university called University of Toronto. Some of you may know him, Adam Hinks. So there's 5 right there. It's the range of whatever people are interested in, they get to do. Way in the back, yeah. Yep. We've already done somebody in the back, so I'm going to. We already had you. So the woman in the front. Yes.
What's your perspective on the search for extraterrestrial?
The search for extraterrestrial intelligence. There's an outfit called SETI. They have an advisory board, a science advisory board, and I'm a member of that board. And as a scientist, my goal is to make sure that the science they do is science that is cool science, whether they find it or not. Let me give you the example of the opposite. Not that I'm criticizing the guy who did the survey, a guy named Ted Peters about 10 years ago, surveyed people of various religions. What would you think? How would it affect your faith if we discovered extraterrestrial intelligent aliens? And universally across every religion, people said, if we found ET, it would show I was right, regardless of your religion, including the atheists. And the fact that we haven't found any intelligence yet hasn't, shaken their faith. So in other words, it's not a critical experiment. The science that they're doing at the SETI Institute is about extremophiles, which is fascinating in itself. It's about looking for extra, solar planets. It's about what are the conditions necessary for life. And it's great science. It's motivated because we'd love to find life. But you also have to remember the really exciting thing, if we found intelligent signals from a star 200 light years away, is not that, oh my gosh, we can learn things from them, but it's that, oh my gosh, there's life. It happens to be giving off radio signals, but there's life. We haven't even found bacteria yet. It's the easiest way to find life around other stars. We're not going to learn anything from them because if you try to send a signal there, it's going to be 200 years to get there, 200 years to go back. What was that again? But just to be able to find bacteria. My master's thesis at MIT was the first detailed models of the icy moons of Jupiter, Europa, that I'd love to be able to go to. And it came up with the model of the icy crust, the rocky core, the water in between. I got the right answer for all the wrong reasons, but that's science. But since 1975 and my science fictional dreams, I've wondered about, what if there was an intelligent tuna swimming in the oceans of Europa, not knowing that the universe was any bigger than the roof and the bottom, because that crust is really thick. And are we like those tuna, living in a universe that has limits that we don't even recognize? There's my thoughts about extraterrestrial intelligence. Let's bring it on. And then in the front, you had a question, yeah.
So I read that in your academic career, you've also pursued theology. And so I'm wondering, did you find that the ways in which you were thinking when you studied theology or in the philosophical context, that it helped you when you were doing the physical research?
Does the theology help the physical research or vice versa? Well, the reason I did theology and philosophy is when I joined the Jesuits, they made me. And it was great. It was really a wonderful experience. But they're tough. Philosophy is not just sitting around BSing. It's a real academic subject with tremendous rigor. And I have tremendous. The first thing actually where my science helped me in theology and philosophy was philosophy is like mathematics and theology is like science. In philosophy or mathematics, if you imagine it, it's real. In science, you're hoping you're actually figuring out what the one universe that we're in is really like. I'm not dreaming up in theology all the possible gods. I'm trying to figure out which description comes closest to the God that I have evidence for. But the deeper issue really is the theme of this. Why do I do it? I talk about the joy I experience. But a person of faith, a person who's in a religion, knows that it's a code word. When I experience joy, I feel God looking over my shoulder. When I plotted up the density, the grain density of meteorites versus their magnetic susceptibility, and I found the different ordinary chondrite classes immediately sorted themselves into different parts in this line. And I don't know if there's anybody in the room who understands a word of what I just said. And there's only 5 people who probably followed that. I don't care. I had that burst of joy that made me feel like God was saying, isn't that cool? Did you see what I did there? Let me show you the next one. And in getting that sense of the Creator's personality, by seeing of all the ways the universe could be made, this is the way the universe was made. That makes me feel a lot more intimate with and comfortable with the Creator in my understanding of it. I think most scientists realize the elegant theory is the one that's going to be closest to the truth, but how do you measure elegance? That's how you measure elegance. That's how you measure what the rightness, the goodness that gives me joy. Yes. Okay, right in the back. Okay. Well, you've asked already, right? Oh, it's the other guy with glasses sitting in the back. Got it. Sorry about that.
Last month there was a meteorite event outside of Cleveland.
Right.
And I think a number of us go through, nuclear bombs and how to identify a meteorite. There's various things.
Mhm.
But the photos of the meteorites that people found after this event all had an outer coating of these very fine bubble-like vitrified hairs. And I've never seen anything like that before. Is that something that I missed, or is this something that seems
Right.
rare?
So to repeat that for the people online, the meteorite fall, the samples that were found of the meteorite fall in Cleveland showed this very detailed and unusual fusion crust. I was actually in Cleveland last week. I didn't see the pieces, but I saw the pictures of the people who had taken the pictures of the pieces. And yes, it's extremely unusual. The difficulty is that most of the time, we don't get to see meteorites that fresh. And within 48 hours of being in the Earth's atmosphere, the water and heat will destroy a lot of that fine. The most spectacular example of that was 2 meteorites that seem to be found within a year of each other, Monahans and Zug, that they found meteorites with tiny crystals of salt and drops of water, actually liquid water, inside the salt, inside the meteorite. And if that rock had been on the ground and the first rain would have washed it away and you never would have seen it. So that's why it's really exciting to be able to pick up a meteorite almost immediately after it's fallen, because there can be these really fine details to it that get lost. Just because, and that's another reason why you go to an asteroid and pick it up there, rather than waiting for it to come to us. No, you do both, but yeah, it's very exciting. It's a really weird fusion crust. You're absolutely right. Oh, from this side, right? Okay.
Teresa here. Thank you for being here. Some 25 years ago, I came here with my daughter with a girls' science club called Vegas, and we went to see in the bowels of U of T this machine that measures meteorites.
Mm-hmm.
It was like some huge zigzag thing. Does it still exist?
Okay, the measurement machine that you're talking about, I think I know the machine you're talking about that you saw 50 years ago. It's probably a variant of a mass spectrometer. And this is how it works. And there's a story to the end of this. You take your little sample and you boil atoms off, atom by atom, in a vacuum. And the atoms, as they get boiled off, are ionized, which means they have a little charge. The electron went away and they're just positive. And in the boiling, they've got a little bit of speed. Because they have a charge, you can accelerate them down a tube. So now they're whooshing down this tube, and if it's a vacuum, nothing's stopping it. And you have another magnetic field parallel, which will bend their path. The more massive they are, the harder it is to bend the path. So that atom by atom, you're measuring out this one's hit here, and those ones went a little bit farther before they hit, and you can calculate the masses of every particle you boiled off that piece of rock and come up with phenomenally precise measurements, not only of the elements, but the isotopes. You know, this nucleus had oxygen with 2 extra neutrons. It was an oxygen 18, not a 16. This is, it allows you to do incredibly precise measurements, which, among other things, says, these are the isotopes that we theorized were made in a supernova or in the collision of black holes, whereas these are the ones that are made in the fusion and steady fusion inside of a star. So, 40 years ago, people have discovered meteorites. A few of them elsewhere, but certainly in Antarctica. All the meteorites in the asteroid belt are 4.5 billion years old. These are only 100 million years old. All the meteorites that we have in our collections are rich in iron because they haven't had much oxygen. These don't have any pure iron. All the iron's been rusted. And in fact, there's carbon dioxide in the minerals. But they're meteorites. You can tell they've been exposed to space, they've been exposed to cosmic rays. Where the heck did they come from? Earth continues to make rocks because it's big and it's warm inside. The moon made rocks for 1 billion years longer than the asteroids because it's small, but it's still big enough that it held its heat. These rocks came from a body bigger than the moon, smaller than the Earth, that has carbon dioxide. Can I think of any body like that? I can only think of one body like that. But what are the odds that you actually got it off Mars? And some theorists had worked out that this was impossible. You can't get rocks. In one of these rocks, looking at it, they realized it had been shocked, whatever knocked it off and caused it to crack. When it cracked, the rock melted. And when it melted, it immediately froze again. Well, what's glass but melted silica? This created a thin piece of glass running through the rock. In the glass were bubbles. So I'm going to carve around the bubble, take that piece of glass, put it in my mass spectrometer, heat up the glass, otherwise in a vacuum, until the bubble goes boop, and all of the atoms in the bubble go shooting down the mass spectrometer. And I can measure their composition, I can measure their isotopes, and it turns out to be exactly the atmosphere of Mars. And that's the final convincing, yeah, these things came from Mars. But those machines, I don't have one of those, not just because the machine costs $1 million, but because it costs $1 million a year to run them, to pay for the technician.
And it's not at UT anymore.
No. What was the, it was the isotrace lab. Okay.
My friend did her PhD.
Okay.
We were very fortunate to go see that.
Yeah.
It was just huge.
But the other crazy thing is that things that big become obsolete. And you have ideas become obsolete. Somebody asked me, a reporter, you know, if you believe in the Big Bang, which is, yeah, kind of the best we got going, invented by a Catholic priest, by the way, not a Jesuit. It is possible to be smart and not be a Jesuit. But he says, you know, if that's how the universe was made, how come God has this goofy story in Genesis chapter 1? Why didn't he just say the universe was made 14 billion years ago in a giant explosion of energy? And I said, you know, if that had been the beginning of Genesis, until 50 years ago, nobody would have known what they were talking about. And 50 years from now, they'll say, oh my gosh, that was so naive. If we do our job right. Because that's how science is supposed to work. That's why those descriptions have to be poetry. Because only poetry is timeless. And for that matter, science is poetry. Those Maxwell's equations, that's not light. That's saying that the electromagnetic field acts like the solution to this equation. That's what, simile or metaphor? I always get them mixed up. But it's poetry. Thanks, everybody, for coming. I could be up here talking for hours, but I'm having a great time with y'all.
Well, thank you very much for coming. We have a couple of gifts for you, and we have gifts for you as well. We've set some food up outside. I know it's warm in here. It's cooler out there. We have a problem in this building with the heat. Mathematicians just always it's like in a planetarium, you know. But that was fascinating. So we have some fascinating things for you from the Royal Astronomical Society of Canada. The North Star. This is Northern Star. It's a biography of J.S. Plaskett.
Oh, thank you.
Yeah, it's
I love books.
pretty good. And this one you may want to share with your friends.
Mhm.
I'm not sure, but you know that's.
They make me. That's what the, yes.
Just giving you a story earlier.
Oh, Castel Gianotto. It's a wonderful wine product of Italy. Thank you so much.
That's from Joanne and the RAC. So thank
Right.
you all for joining us.
Yeah, oh yeah.
So I'm sure Brother Guy would love to continue chatting with you outside just through this door, and we'll see you out.
Thanks a whole bunch, everybody.